Good morning. So we'll start. Okay, so last time we discussed the reduction from 3 sets to vertex cover. As I pointed out, it is very important. You must remember that reduction. All right, so now we have 3 problems in our NP completeness seed problems. So we have 3 problems already. Actually, vertex cover problem will be very useful to prove that other problems are NP complete. So today, actually, for the first lecture, actually, I think I will mainly concentrate on reduction from vertex cover to other problems. To give you a taste how we can show NP completeness of other problems by using vertex cover, and the idea involved. Of course, that can only give you a taste. Frankly speaking, it's quite difficult to come up with a proof that a problem is NP complete. It's not easy at all. You really need a lot of experience. You have to do a lot of homeworks. As I pointed out last week or the week earlier, you need to know maybe at least 50 reductions or even 100 reductions to get a feeling of how reduction works. All right. But I think you should have at least a taste or feeling of how reduction works. Okay. So let me start with vertex cover. So let me remind you vertex cover. So we want to find subset of vertices with at most k vertices to cover all edges. All right, so that's vertex cover problem. Vertex cover has a lot of applications, really a lot of applications. For example, in terms of wearing mask. Who should wear mask? Actually, it's really a huge amount of waste in Hong Kong when only a few cases. Millions of people wear masks every day. That's a lot of waste. But if wearing mask, suppose 2 persons in contact, and it's sufficient to protect both of them if 1 person wear a mask. But then the problem is really vertex cover problem. So if 1 person wear a mask, that will protect both people. Then if we know how people interact, then the problem is really a vertex cover problem. So for 7 million people in Hong Kong, we only need to find the minimum size vertex cover since these people wear masks. Of course, it's we don't know the interaction graph. Otherwise, the problem is really vertex cover problem. Okay. That's medical science. I really don't know whether it's true or not, but that's not mathematics or not computer science. Whether 1 person wear a mask will be sufficient or not, that's a medical problem. I mean, once that problem has been solved, then the problem is really a mathematical problem. All right, that's a vertex cover problem. There are a lot of different applications. For example, if we do experiment, if some experiment come with different data, then 2 different experiments maybe conflict each other. So if these 2 experiments get contradictory results, then at least one of the experiments is wrong. Then we have to redo at least one of the experiments to obtain the correct data. Then again, if we have a conflict graph among these experiments, so maybe that's a conflict graph among experiments. All right. Then to determine the minimum number of experiments that need to be redone, again, it's a vertex cover problem. So we do redo some experiments. Maybe in this case, 3 will be sufficient to tell what went wrong. All right. So vertex cover really has a lot of applications. It's a very important problem. That's why in practice, it's very useful, even to show that certain problems NP complete. All right. Now, of course, there are two problems that's basically is same as vertex cover problem. It's vertex cover problem in disguise, namely the independent set problem and the clique problem. So from anti-completeness of vertex cover, we can immediately say these two problems are anti-complete. So it's so if you remember the connection between vertex cover and the independent set, so that stands for independent set. And the clique. These two problems. All right. So relation between vertex cover and the independent set is complementary in terms of the solution. So if you can recall from discrete math, so if we have a vertex cover here, V prime is a vertex cover. So vertices outside of V prime form an independent set. All right. Because these vertices cover all edges. So on this side, V minus V prime side, there are no edges at all. All the other edges may be inside a V prime. So it's possible we have edges here. But on this side, there are no edges at all. So this part is independent set. So if the size of vertex cover equal K, let me use different, no, sorry. So the size of this one, of course, equals n minus k, when n is the number of vertices in the graph. Then there are trivial reduction. If you really want to get to reduce vertex cover to independent set, there are trivial reduction as follows. Very simple reduction. Vertex cover to independent set. All right. So instance of vertex cover will be GK. Then what's the instance of independent set? Same graph. But the size now become n minus k. All right. So we can easily reduce vertex cover to independent set. Actually, they're the same problem, just the size. One is k, one is n minus k. All right. So if we regard this one as G prime, K prime for independent set, so where we have G equal G prime and K prime equal n minus k. All right. So that's a trivial reduction from vertex cover to independent set. So that's pure independent set is NP-complete. Now for clique problem, there is obvious connection between independent set and the clique. A set of vertices, V is independent set if only if these vertices form a clique in the complement graph of G. If we take the complement graph, all right, so because this relation, there is a trivial reduction from independent set to clique. Let me see. Let me draw something here first. So if this graph G and its complement graph G prime, so edges become non-edges and non-edges become edges. So vertices remain same. Okay. So red edge are edges inside. Maybe I use a red graph here. Okay. So we have this edge, this edge, this edge, and cross edge too many. I will not draw it. So some edges, maybe this one and so on. So some edges, but here will become a complete graph. let's see. I may have missed some edge because there should be 10 edges. Still one edge is missing. Maybe this edge. So here from K5 in its complement. Okay. So because there's obvious connection, we have a very simple reduction from from independent set to clique. Independent set to clique. From GK, so that will to it's complement graph, but K is same value. All right. So that's very simple. So essentially, independent set and clique are same problem as vertex cover. So going back to the first page, so we know these two problems are also NP-complete. So now we have 5 problems in our toolbox. So we can use them as seed problems. Okay. Now, because of increase a number of problems in our toolbox, now it may become difficult when we want to choose a right problem for reduction. So to find the best tool is not a trivial task at all. Find the right tool. That certainly depends on experiments. If you consider daily life, when we want to do something, if you want to fix something in your home, whether you use hammer or screwdriver, it depends on experience. If you have enough experience, it's quite trivial. If you don't have enough experience, maybe it will be a problem for you to whether to use a screwdriver or hammer, right? Okay, so I think you can draw the equivalence easily. Okay, all right. So now we'll use vertex cover to show certain problems are difficult, are NP-complete, are intractable. All right, let's see. A vertex cover problem is very useful to prove the following type of problem are NP-complete. For example, if we want to delete K vertices to destroy given structure S, maybe to destroy given type of structure, maybe structure maybe I write as S structure. For this type of problem, typically we can use vertex cover. We can reduce from vertex cover. By so-called local replacement. So typically what we'll do is replace an edge by structure S. So for each edge, we'll replace it by this structure S. So this idea of local replacement, actually there's not much point to classify technique we use for a particular problem into different catalogs. But it may be useful to give you an idea how we can proceed to prove NP-completeness. All right. So one important useful tool is called the local replacement. The following example will show you how it works. For example, the following classical problem. Let's see. All right, so our input will be a digraph. So we have our input as a digraph. The question is, can we delete at most k vertices so graph becomes a DAG? Acyclic means the graph becomes a DAG, a directed acyclic graph. So can we remove k vertices to destroy all cycles? So for this particular graph, a single vertex will be good enough. If we remove this vertex, then the graph has no cycle. So that's a classical feedback vertex set problem. All right. Now it's trivial. The problem is in NP. Remember, okay, it's you can almost always say that the problem is trivially in NP, but don't forget to say it, especially in exam. All right. Because to show it's a problem is NP complete, you need to show it's in class NP first. But that part is typically trivial. So don't forget to say it. Okay. So mainly we can concentrate on reduction to show it's the problem is hard. It's NP-hard. All right. So in this case, reduction is very simple from vertex cover to this problem. And this same idea will be useful for homework 4. All right. So reduction here will be useful for solving 2 problems in homework 4. So what we're going to do is use vertex cover to reduce to this problem. And the construction is very simple. So given a graph G and K of vertex cover, we construct a graph, a digraph G prime and a number K prime so that this one has a K vertex cover, if only if this one has K prime, a feedback vertex set. All right, and this construction have to be done in polynomial time. And usually this part is also trivial, usually, but sometimes can be very subtle. All right. Now, in this case, what we do is give a graph, say this graph. What we do is to replace each edge by a cycle, a directed cycle. Here, the structure S, this structure S, it will be a directed cycle. But in this case, it's a very simple directed cycle. It's just 2 edges, a diagonal. So G prime will be obtained from G by replacing each edge by a diagonal. All right. So here our resulting graph, if we do this replacement, so our graph will look like this. Okay, almost just enough space. So from G, we get G prime. And we set K prime same to be K. All right. Now, the connection actually very simple. Here, vertex cover, maybe in this case, C3 vertices form a vertex cover for this graph. Now, vertex cover will destroy all edges. So that means because each edge corresponding to a diagonal, so if we use these 3 vertices, that will destroy all diagonals. Because each diagonal corresponding to an edge, so it will destroy all diagonals. Yeah, it's a cycle of length 2 called diagonal. Di means 2. No, without a, diagonal. Di is same prefix as bi. Bi is a prefix, means 2. Di also means 2. All right. Okay. Yes, that's right. Carbon dioxide. Great. Yeah. Okay, that's a prefix. Right. Okay. So since each vertex will destroy all diagonals, all edges, so therefore it will destroy all diagonals. Now, the important thing to note is in this graph, all cycle, any other cycle, of course, we have other type of cycle. For example, we can have this type of cycle in this graph. But this type of cycle also involve edges. or in the original graph. Because vertex cover destroy edges, so it's impossible once we remove the red vertices, we still have a cycle because some edge in the cycle will be covered by a red vertex. So therefore, we cannot have such cycle left once we remove red edges. All right. So leave detail for you to convince yourself. So after class, I really suggest that you really convince yourself why it is the case, or maybe even you want to try a rigorous proof. So that to prove this one rigorously, then you will see why it is the case. Then it will really help you to solve the homework problems in assignment 4. Okay. Now the key idea here is so-called local replacement. So we uniformly replace this structure by this structure. So we don't care about their connections, just uniformly replace it. Each edge will be replaced by a diagonal. So that's a typical local replacement. Actually, I have seen it earlier when we do a reduction from set to 3 set. That's also local replacement. We uniformly replace each clause of a certain size by a collection of triples. Okay, so that's the idea of local replacement. It's very useful. For some simple proofs, of course, difficult proofs usually involve more things. All right, so that's one example of reduction from feedback vertex set. From vertex cover to feedback vertex set. Okay. Next problem is the following one-sided domination problem. One-sided domination set problem. What we have as input is a bipeptide graph. So we want to find out, so it's, we have a bipeptide graph. So one side is X, another side is Y. Both are independent set. All edges are these type of cross edges. So that's a bipeptide graph. Okay. The question is, can we find at most k vertices on one side? Such that every vertex on Y side has at least one neighbor inside X. So that's the one-sided domination part, dominating set problem. So we only choose vertex on X side. So for example, for this one, I may need 3 or 2. I guess need 3. So if I choose this vertex, so that will dominate this one, this one, this one, this one. All right. Now if I choose this vertex, it will dominate this one. So some will be dominant Y, more than one. If I add one more edge, then 2 will be good enough. Since these 2 vertices will dominate all vertices on this side. Okay, so it's a one-sided domination problem. As the problem, again, it has a lot of applications in practice. For example, consider lunch, okay, a student canteen, for example. So one side, X may be different type of food, different type of food. Maybe it's X side. So maybe pork, fish, egg, some kind of vegetables, maybe potato. All right. Other side is students. So this side is students. All right. So the link between an edge between the food and the student means the student likes that food, can take that food. All right. Now, of course, it's quite easy to see that canteen cannot provide too many food, say for lunch, maybe 10 varieties, 20 varieties at most. All right. So the problem is really, can the canteen produce 10 different, maybe 10 different kind of food to fit needs of every student? So that's one-sided domination. So the problem is really very useful in practice. All right. Okay. So unfortunately, this problem is also NP-complete. So next time you go to a restaurant or canteen, don't complain too much in case you cannot find the food you like, because the problem actually is very difficult for them to come up with small number of variety to fit the need of everyone. Okay. All right. So we can prove that this problem is NP-complete by reduction from vertex cover. One-sided domination. All right. So again, the idea is by local replacement. No, it's really not easy to come up with a reduction by yourself quickly. You really have to understand the problem in order to give an NP-completeness proof. Otherwise, it's not easy at all. You have to fully understand the problem. Otherwise, it's difficult. So you have to make a similarity between these problems. So these two problems may be totally different. Like vertex cover and one side of domination, actually they look quite different. Somehow you need to find the similarity and then try to explore the similarity so we can come up with a reduction. All right, so the idea here is the following. So again, we have a graph G and the K. We need to construct a new graph G prime and the K number K prime. So where this one is a bipeptide graph. Just say bipeptide, okay, it's easier. Okay, so actually reduction is very, very simple. Now vertex cover, what happens is vertex cover, it's a relation between vertices and edges. So that's vertex. And edges, the UV, that's edge. Vertex cover, we're really talking about relation between vertices and edges. We use vertices to cover all edges. Right? Now, so that's one. This structure can be viewed as the following: U, V. So suppose that's edge E. Say U, V. So if I draw it in this way. Now for this is the graph on the right hand. So actually it's this vertex dominate this one. Do you see the connection now? Once I give this one as a hint. So now what happens is this. So for a graph, all right, so what we do is we construct a bipeptide graph where vertices inside V will be X side. So X side will be vertex V. Y side will be edge set. So what happens, actually we insert a vertex for each edge. So that's graph G prime. And we can also use vertices, blue vertices, to dominate red vertices. So if I draw it in another way, it's maybe more like this one. I can draw it in this way. So will be maybe write V1, V2, V3, V4, V5. Okay, so we have V1 here, V2. All right, now V1, V2, this edge. Red one, V1, V2. So that's this edge, V1, V2. So we have connection here, V1, V2. V2, V3, similarly, that's V2, V3. A V1, V4. A V3, V4. And V3, V5. Now see, that's a bipeptide graph. And the vertex cover really become here one-sided domination in this new graph. So let's use this color. So this vertex cover is corresponding to this one. V1 covers these two edges. So here dominates these two vertices. All right, so you see the correspondence. So that's how this reduction works, from vertex cover to one-sided domination. So again, the construction is very simple. Locally, we just replace an edge by this edge. Oh, that's a, no, one-sided. I just shorthand, one-sided, 1SD, okay, one-sided, shorthand. No, K prime is same as K. K prime is exactly same as K because the vertices we use for G prime is exactly vertices in the vertex cover on X side. We use vertices on X side to dominate, so it's exactly these two vertices. For Y, X, other vertices on X side, we don't care. We only need these vertices to dominate Y side. Each vertex will dominate an edge. So each vertex will dominate an edge in the original graph, which is the vertex in the new graph. So each vertex here each vertex represents an edge. So each vertex on the Y side is an edge in the original graph. So V1, V2 will correspond to this edge. Now, in vertex cover, the solution size, here K prime is solution size. So number of vertices on X side, which is exactly K. Okay. All right. Okay, so that's a reduction. So again, we use this local replacement. So these two easy examples should give you an idea how we use vertex cover to prove problems. In particular, we need to find the K vertices to destroy a particular structure S of type S. All right. Okay. So like odd cycle, sorry, not odd cycle, direct cycle in feedback vertex set. Actually, in vertex cover, we want to find K vertices to destroy all edges. In vertex cover problem, actually, we want to destroy all edges by using K vertices. Okay. All right. Okay. So next example now is dominating set problem. It's a general dominating set problem. Again, it's a very fundamental problem and extremely useful. So this problem is exists K vertices, at most K vertices, such that so it's more general than one-sided domination. One-sided, we only use a vertex on one side. But in general dominant set, it's not a bipeptide graph. It's a general graph. All right. So for example, so if we choose a vertex here, so it will dominate this vertex, this vertex, this vertex. All right. So if we choose this vertex here, it will dominate this vertex and this vertex. So in this case, I guess solution is still 3. I also need to choose this vertex. All right. So if I make a comparison between vertex cover and this one, so vertex cover vertices cover all edges. So there may be edges here on this side. And for dominating set, maybe it's on this part. Does not matter. Okay. Oh. Now the difference between vertex cover and dominant set is dominant set we can have edges on this side. But for vertex cover, we don't have edges, so no edge on this side. Dominant set can have edge. Has, okay. Inside, we're allowed to have edges. So that's the only difference. Okay, so the vertex cover dealing with relation between vertices and edges. Dominant set relation between vertices. So we're allowed to have edges on this side. And the vertex cover is a special case of dominant set. So if V prime is a vertex cover, it is also a vertex, it's also a dominating set if graph has no isolated vertices. When graph has no isolated vertices, vertex cover is also a dominating set, but not vice versa. So in a sense, vertex cover is a special case of dominating set in terms of solution. So every vertex cover is a dominating set when graph has no isolated vertices. Because if it has isolated vertices, then we may have this situation. Since these two vertices are not dominated by V prime. Okay. All right. Okay. So now what we are going to do is give a reduction from vertex cover to dominating set. Again, by the idea of local replacement. So what we do again is to replace each edge by some structure. So each edge will be replaced by some structure here. So some structure. So from an instance of vertex cover, we get an instance of dominating set. Now, in this case, you will see that this K prime does not equal K, will be something different. Very often in the reduction, this K prime will not be equal to K. So this example will show you that indeed, we have example where K prime will be much larger than K. In previous two examples, K prime equal K. All right. Now, this H is not unique. There are many ways to construct this gadget. One way is we can use the following in the nodes, same in the nodes. UV, each edge, so UV will be replaced by this structure. Or we can use other structure. In this one also works, or even this structure, an easier structure will also work. But in terms of proof, maybe actually it's easier to use this one to prove it. This one, the last one, a path of length 4, it's the most simple one, I think. Okay. But in terms of proof, maybe this one is a little bit easier in the argument. Right? Now, why this one works? Let me explain. So what happens is this K prime now will be set to be number of edges in the original graph plus K. Okay, so reason is as follows. So let us forget about the last two possibilities. We just use this one. So here's the idea. Why we use this one in the reduction? So what we do, replace each edge by this gadget. So what happens is in a vertex cover, so we cover this edge by one vertex. So in terms of dominating set, what happens in this one, we can use this vertex that will dominate this vertex. Now for remaining vertices, we'll use one inside. We use this one. So that one will dominate these three. Okay, so that's a comparison of the correspondence between vertex cover and dominating set. Whenever we can cover this edge by vertex, we can use two vertices to dominate this gadget. One vertex is same as vertex used in the vertex cover. So these were same. And then one uses one vertex inside, one internal vertex. Always one internal vertex. So for each edge, we use one internal vertex. Therefore, we have M here. And it's also necessary, if we look at this graph again, we always need to use at least one internal vertex because of this one. Now look at this part. How can we dominate these vertices? These two vertices will not dominate these four vertices because these two are inside. So we need to use at least one vertex among these four to dominate these four vertices. So therefore, each edge will need at least one internal vertex. So this gives us number M. All right. Now, it's quite easy to see that any k vertex cover will give us dominant set of size M plus k. We use vertices in the vertex cover plus each internal vertex for each gadget. All right. On the other hand, typically one side is trivial, another side you need to be careful. So in this case, it's also easy. On the other side, any dominating set of size M plus k, each will use at least one internal vertex. So we can argue that it will use at least one vertex inside. So if it dominates in this way, then I can use this vertex in the vertex cover. Because whole gadget contains, so for this whole gadget, it contains one vertex. So that means that vertex can cover this gadget, therefore this edge. But it may be the case we have this situation. The solution may look like this for a dominating set. Instead of that one, it uses these two vertices. All right, so in this case, what we need to do is transform the solution to a different one. So in this case, this one is solution, but this one can be transformed into this solution. Actually, inside, we don't need two vertices. Instead of use this vertex, we can use this vertex. It's also give a dominating set. By doing that, then we have a dominating set that use exactly one internal vertex. Then after that, we can get a vertex cover. Okay. All right, so I think it's almost time for auxiliary teaching evaluation. I think I should almost stop. Okay, a few words. It's very important to get yourself familiar with size of small of vertex cover of small graphs, such as like a triangle. How many vertices we need to cover all edges? K4, a complete graph. How many edges we need to? How many vertices we need to cover it? So it's very important to get yourself familiar with these things for the sake of homework and also final exam. All right. So this one will need 3 vertices to cover it. This one too. In general, for complete graph on k vertices, we'll need n-1 vertices to cover it. Also, for some graph like this, star, we only need 1 vertex to cover it. So it's very useful. You must get yourself familiar with these small graphs. As I said, it's very useful for homework and the final exam. In terms of final exam, let me tell you, you need to, it's not easy to get above 80%, 80 marks. It's not easy, but it's okay. It's possible, 80 or even 90. And you really need to work very hard to get below 50. I would be really surprised if you can get like 40 marks or 50 marks. If that's the case, perhaps you really should think whether you should change your major. Okay, when I design these exam questions, basically I have a very good idea, like on average, how much you can get. So for this final exam, I think I am for about 65%, 65 marks out of 100. And it's really, very difficult to get below 50. It's anti-hard, all right? Okay, I think I should take a break. I think uh, Sylvia, I think she's in now. Let me see. Are you in? We have a staff from general office to do teaching evaluation things. Hi, Sylvia, are you in? She's supposed to be in now. Let me check. Sylvia. I don't know if she's supposed to be in. Anyway, stop the call.